Hi, let's talk about Geiger Muller counter. The Geiger Muller counter was invented in the year 1928, a long time ago. And even today, this amazing instrument is widely used for the measurement of radioactivity. First, let's see the construction. The construction of Geiger Muller counter is quite simple. It has a metallic cylinder with a wire in its center. Now this wire is placed in such a way that the insulator is placed in the middle. This insulator prevents the direct connection of wire with the cylinder. The cylinder is filled with an inert gas such as argon or neon, and they are placed at low pressure. The mouth of cylinder has a thin window of mica. This is to allow the entry of radiation in the cylinder. The metallic cylinder and the wire is connected with the power supply. The cylinder is connected with the negative potential while the wire is connected with the positive potential. Now let's see the working of Geiger Muller counter. When the ionizing radiation comes in the cylinder, it interacts with the argon atoms and causes ionization. During this process, an electron is removed from the argon atom. Since the central wire has a positive charge, the electron is attracted towards the central wire. This electron will give rise to electric current. However, here is the catch. The electric current of the single electron is negligible to detect. To solve this problem, scientists thought of increasing the potential difference between the cylinder and the central wire. The increasing potential difference increases the electric field. Because of this, the electrons get accelerated towards the central wire. The accelerated electrons have more energy. When the accelerated electron collides with other neutral argon atoms, these atoms also get ionized, producing an electron. This process again repeats, producing more number of electrons. This phenomenon is known as Townsend Avalanche effect. Now let's understand this phenomenon in the form of graph. This small gap over here represents the situation where the number of electrons are very less, hence no current is detected. With an increasing potential difference, the current increases. Now this happens until a certain point is reached. After this point, there is no longer increase in current. The graph over here becomes flat. Now let's try to visualize this. Why does the graph becomes flat after this point? Now with an increasing potential difference, you reach a point where all the argon atoms are ionized. This is the point where you have maximum number of electrons generated in Geiger Muller tube. This ultimately results in maximum current as shown in the graph. This is the region where Geiger Muller tube is operated. Always remember this. It is operated in this region where the entry of one ionizing particle will ionize all the argon atoms by Townsend Avalanche effect. This results in maximum number of electrons and maximum current. Now let's see what happens when everything in the Geiger Muller tube is ionized. When everything is ionized, if by chance, if alpha particle or beta particle enters the tube, it will not be detected. Let me repeat this again. When all the argon atoms in the tube are ionized, the entry of radiation in the tube will not be detected. This is because there are no neutral argon atoms left. This is also known as dead time of Geiger Muller tube. Let us understand this phenomenon in detail. The positively charged argon ions travels towards the negatively charged cylinder. Since the cylinder is negative, the argon ions, upon reaching the cylinder, gains the electron and again becomes neutral argon atom. Now it takes roughly around 100 microseconds for all the argon ions to gain an electron and become argon atoms. So in the small time interval of 100 microseconds, if any radiation enters the tube, it is not detected. This is because all the argon atoms are not yet ready for another round of Townsend Avalanche phenomenon. Now, after about 100 microseconds, the Geiger Muller tube is again ready with neutral argon atoms. When another ionizing particle comes in, again there is a Townsend Avalanche effect, which causes production of ions and electrons. Now the question is, what is the maximum number of ionizing particles that a Geiger Muller tube can detect? So if we see the mathematics, then after every 100 microseconds, the Geiger Muller tube can detect one ionizing particle. This means in 1 second, it can roughly detect around 10,000 particles. And in 1 minute, this will be around 6 lakhs particle, which will account for 6 lakhs counts per minute. So this is a maximum number of ionizing particle which a Geiger Muller counter can detect. Before we end, let's go back to our graph. The last part of this graph, which goes straight up, is known as continuous discharge. This means at very high potential difference, there is an arc which is generated between the wire and the cylinder. This results in sudden increase in current, which is also known as continuous discharge.